Okay, this is my second video from section 7.1, and we're going to talk specifically about the normal probability curve. Normal probability curve, you know what it looks like. Oopsie. We have a horizontal line here, and above that we have something that looks something like a bell shape. This horizontal line here, the data is on here, on the x-axis. Because that's right, it is an x-axis. These are Cartesian. This is a Cartesian grid here. The y-axis isn't showing up because I don't actually care where the y-axis is because height doesn't matter for me. But that does mean here that this curve here has a function that defines the shape of this curve. And are you ready for this? This curve is e to the power of -1/2 times x minus mu divided by sigma, and all of this is going to be squared, and all of this is going to be divided by sigma times 2 pi. So in other words, yikesies. And what we would do to find the area under this curve, well, clearly with a function like that, this is a little bit of geometry that's well beyond us. What we would normally do is use calculus, and we would find that the area of the probability as x is bigger than a and less than b is equal to the integral from a to b of this function up above. So you might have noticed this is beyond the scope of this class. So instead we're going to let people who are cleverer than us and have a heck of a lot more time on their hands than we do figure out all of these integrals. Now what they used to do is they put them on a table, but that's very old school. In the same way that we don't use log books anymore to compute logs, we don't need to use tables anymore to compute the area under the curve. Instead, just like logs, we're going to use a calculator. So in order to use our calculator, we do need mu and sigma, but that's all we need. All we need, we need for a normal probability distribution is the mean, mu, and sigma, the standard deviation. And because if I know mu and I know sigma, I know everything I need to know about the shape of my distribution. So here's a question: why? Let's talk about sigma first. Now, what we know about sigma, pretty much, well, it measures variation. Here's the mean. And we know that 95%, almost all the graph of the data is between the mean minus 2 standard deviations and the mean plus 2 standard deviations. So if I went down 1 standard deviation and then down another standard deviation, if this distance here is a standard deviation, I'm going to cover almost all of the graph. And if I go up 1 standard deviation and I go up another standard deviation, what we have here is 95%, which is also translates into 95% of the probability is that part of the graph there. So if I increase sigma, if I have a large standard deviation, what is that going to do to the graph? Hang on, let me clear the screen. If sigma gets larger, then what we're going to end up with is, here's the mean. Oh, please work. Here's the mean. But if the standard deviation gets larger, it's going to take 2 of these to cover the entire graph, or almost the entire graph, 95% of it. So what we're going to end up with is a much wider graph. But if I have a wider graph, I'm also going to get a shorter graph. Why does wider mean shorter? Because total area is always 1. No matter how wide it gets, it can't cover an area bigger than 1. So if it gets very wide, it also has to shrink. If I have a small standard deviation, here's 1. With a small standard deviation, the whole thing got a lot smaller because I'm running out of room here. It has to get taller. Hang on, let me clear the screen. So let's recap here. The standard deviation controls width. And so what people tend to think is, well, mean must control the height. No way. Standard deviation controls width and height. Big standard deviation means wide, and it must mean short. Small standard deviation means narrow, not very wide, which must mean it's tall, because total area is always 1. So what does the mean do? It does exactly what you think it does. It determines center. But let's put two graphs next to each other that have the same standard deviation but have different means. Sorry, I got a little blurry when I blew it up to fill up the screen here. But this first one, the pink graph, the mean here, the mean here is equal to 0 of the pink graph. And of the blue graph, the mean is equal to 3. They both have the same standard deviation, so they have the same width as each other, they have the same height as each other. So what the mean does is slides it along the x-axis. So what I want you to do now is I want you to stop the video and I want you to do example 4 on page 362. And there's a little bit of reference there to inflection points. Well, we're not covering inflection points in this class, so ignore, it's in the explanation of the example, the bit about inflection points. If you've had calculus, that will have some information, some meaning to you, but if you haven't had calculus, you're not expected to have run into inflection points before. Okay, the last thing I want to do is review the properties of a normal density curve. And so just so that we're all clear that this is the information that you need to know about a normal density curve, also known as the curve that defines a normal distribution. So bell-shaped, so you have a rough idea of the shape of it. Unimodal, yes, if it's bell-shaped it has one peak, but let me emphasize that that peak is going to be at the mean. Oops, I have the eraser on instead of the pen. That's where the peak is. Because if you're a bell curve, you are symmetric. And so if it's symmetric, we know that that means that the mean will be at the center. And the total area of your probability density curve, what does that equal? Please say it with me. It will always add up to 1. It doesn't actually matter if it's normal, not. The area of any probability distribution will add up to 1. And the whole graph can be determined by mu and sigma. This gives you the center, and sigma tells you not only the width, but also the height. And then there's one last thing on here. I have skipped the empirical rule this quarter, so I'm only mentioning it if you've run into it before. If you know the empirical rule, this can be used to define a normal curve. You can define it if it matches the description of that formula, e to the negative 1/2 x minus mu over sigma quantity squared divided by sigma 2 pi, or if it obeys the empirical rule. But other than that, that is all I'm going to say about the empirical rule this quarter. So you can disregard this if you haven't run into the empirical rule. So that's all I've got to say about section 7.1.